Hi and hello everyone. I'm Shamini Manimaran and my matrix number is 229945. And today I'll be presenting a brief technical overview on understanding fluid properties and their engineering applications. And I'll be focusing on three key fluid properties, which is viscosity, density, and surface tension, and how they influence real world engineering systems. I will also highlight a design conflict where these properties interact and require trade offs. Fluids are everywhere in engineering, from pipelines and aircraft systems to biomedical devices. To effectively design systems that involve moving or storing fluids, engineers need to understand how fluids behave under different conditions. That behavior is largely governed by properties like viscosity, density, and surface tension. These properties affect flow, pressure, force, and interaction with surfaces. Next is the three main key fluid properties. Firstly, its viscosity, which is the measure of a fluid's resistance to flow. Think of how slowly a honey pours compared to water. That's due to its high viscosity. In engineering, viscosity affects pumping power, energy losses, and the sizing of piping system. Next is density, which refers to how much mass is packed into a unit volume. It's especially important in aerospace and maritime engineering, where weight, buoyancy, and pressure changes matter. For example, jet fuel density affects how much fuel can be carried and how its influences flight range and balance. And lastly, surface tension. Surface tension is caused by a cohesive forces between fluid molecules at the surface. It plays a major role in small scale systems like microfluid devices and capability actions. Engineers rely on it for accurate fluid control in medical, diagnostic, and drug delivery systems. General applications which are general, for example, oil pipelines in which viscosity affects pump energy, density affects pressure and buoyancy. Aircraft fuel systems in which fuel density influences flight balance, capacity, and safety. And lastly, biomedical devices in which surface tension and viscosity impact drug delivery and diagnostics. Now, let's look at a real world application that involves all three properties, which is viscosity, density, and surface tension, which is inkjet printer design. These printers are used in everything from everyday printing to precision medical devices that dispense fluids. The goal is to push fluid through the tiny nozzles while also forming clean and precise droplets. This also requires a balancing in both viscosity and surface tension for high performance and accuracy. But here is the conflict. Lowering viscosity helps the fluid to flow easily through the nozzle, but doing that often reduces the surface tension, making droplets unstable or poorly formed. If you increase the surface tension for better droplet shape, it will become harder for the ink to flow, leading to nozzle clogging. And how does the engineers solve this conflict? Engineers overcome this through several strategies. Firstly, they'll be using specially formatted fluids with surfactants to control viscosity and surface tension. Secondly, they apply slight heating to reduce viscosity without drastically changing surface tension. And thirdly, they design the nozzle geometry to balance flow dynamics with droplet precision. To conclude, understanding fluid properties is essential to engineering systems that rely on flow, pressure, or precision fluid control. Viscosity, density, and surface tension may seem really simple, but their impact on real world design is significant. The inkjet printer is a great example of how much these properties interact and how engineers resolve trade offs using smart material choices and design adjustments. And that's all from me. Thank you.